Hi everyone, I'm Brenda Valdez.
I'm Brandon Neri.
I'm Robert Bond.
All right, so our problem identification is that we need a feasible way to actually explore and gather data outside of the heliosphere. Thus far, this has been done very few times, and there's a lot more data that needs to be gathered and more efficiently, and that is the purpose of what we are trying to do. Some of the requirements that we had to get done, some of the purpose, is that we need to be able to deliver a 50-kilogram payload to interstellar space within 20 years, and then have that payload stay out there, still exploring for another 20 years, sending back data to Earth.
So this mission is very significant. It will allow us to attain more in-depth knowledge about the interstellar medium and interstellar space, as well as the edges of the heliosphere. And acquiring this knowledge is going to help us in the future development of methods of travel for interstellar flight, as well as flight within the solar system. And this can increase our potential for future interstellar missions that might be manned as well as automated. And some of the difficulties or challenges we face in this mission are the difficulties associated with space travel, with it being a hostile environment, and the particular difficulties associated with the distance we're covering. Because of the vast distance, communication with the craft is going to be difficult. Its maintenance is going to be difficult, especially because we can't physically interact with it. And also the very uniqueness of the mission makes it challenging, because there are so few prior examples we have that we can build off of.
So our project will achieve heliosphere departure in no more than 20 years, allow for us to improve upon sensor system accuracy and resolution to provide better data on the interstellar medium, and finally improve upon the longevity of previous interstellar probes.
So, in order to design this, we had to base our design off of similar concepts and ideas that have already been done. Most notable among these was the Voyager 1 and 2. They have both crossed into the past the heliosphere, and have still been sending back data to Earth. Now, what we need to do is not the same. We actually need to improve greatly upon the Voyagers, almost having the time it took for them to cross out of our solar system and into the greater interstellar space. And that is the entire goal of what we are doing, and we used a lot of information from the Voyager 1 and 2 in order to make this an easier and much more sound process, just improving upon them and making it our own.
So we began improving on the Voyager concept by designing our own operational concept. The full thing is laid out here, but it can be divided into 4 phases, which were shown previously. The first phase is departure of the craft from the Earth's gravitational sphere of influence. The second phase is going to be the traversal of the heliosphere, which we have stated will take no more than 20 years for our craft. The third phase is going to be departure from the heliosphere and crossing over into interstellar space, where it will continue flying for 20 additional years. And then there is a constant phase throughout all 3 of these previous ones, where whatever we send out is going to be collecting data constantly and communicating it to Earth.
So as far as our system goes, we are able to break it down into 3 elements, and then from those 3 elements into various subsystems. The 3 elements are the actual launch device itself, the data collection facility on Earth, and the probe. So for the launch device and some of its requirements, that it needed to be able to launch the probe with a velocity and acceleration that will enable it to reach the edge within 20 years. As far as the data collection goes, it needs to run for 40 years, constantly collecting data from the probe and being able to interpret and maintain that data, and then send out the data that it collects to the greater world. And as far as the probe goes, it was broken down further into data collection, which it'd be collecting data, taking pictures, infrared, ultraviolet, magnetic data, and a few others, just to gather all of it and be able to give us a holistic picture of space past our solar system. Another one is the actual propulsion system and navigation system, where it's going to be broken down so that it can actually make it there in time and then avoid obstacles along the way. It needs to be launched in such a way that it's not going to hit anything, and that it is going to be able to maneuver itself around what is out there. And it also has the communication systems, it needs to be able to communicate back constantly back and forth with Earth. And the last subsystem out of all of them is that it needs to be powered for that whole time. The power is going to be sent out and collected by it. It is going to be self-generating, and it has to power the data collection as well as the propulsion for the entire period of its life cycle.
So, when designing our probe, a TOPSIS trade study was done on the method of propulsion. The TOPSIS trade study allows us to weigh different criteria and compare multiple solutions to our problem. For our probe, our decision was based off of the precision of the propulsion system, the weight, speed, cost, and longevity. So after qualitatively scoring each of the different propulsion systems, it was decided that ion thrusters would be the best propulsion system for our probe. They are cost-effective, precise, fast, and dependable. And while the Voyager 1 and 2 missions previously used chemical propulsion, electric propulsion has come a great deal in terms of research in the past 40 or so years and are currently the preferred method for deep space travel.
So after conducting this trade study, we set about designing an early function architecture, which is here, and some of its main features are highlighted on the right. The most important one is, as Brenda just mentioned, the main propulsive subsystem we were going to be using are electrically driven ion thrusters. And another important point is the electric power for the craft is going to be derived from radioisotope thermoelectric generators, which are very good at producing electrical power in regions where you cannot rely on things like solar energy, which we're going to be operating in. This is a morphological matrix, which is an example of tools we used to examine different alternatives that were available for our subsystems. And this is the revised concept architecture we arrived at after analyzing some of these alternatives, and some alternate angles of that revised architecture. On the top left, the probe is depicted flying into the page. On the bottom left, it is flying out of the page. And on the right, it is depicted to scale with a potential launch vehicle, and its components have been oriented or compacted in order to fit in the payload segment of that launch vehicle. And so there are several merits to our revised architecture, and we understand that the total mass of the craft we have designed is going to exceed previous craft designs for comparable missions like the Voyagers, but it's going to offset this by utilizing less massive sensory systems and electronics, and it's going to do that in conjunction with the use of alternative propulsive systems. So in the end, it is going to achieve greater heliospheric escape velocities and get to the heliopause faster. And it's also going to be simple enough that we can compact it into a launch vehicle without unnecessary difficulty.
So the financial projection was come to a total of $745 million, and this was arrived at after doing the math for the personnel as well as the materials and the research and production cost of the entire device. Our potential customers are really just the U.S. government, because this kind of project would likely be a joint venture with NASA in order to actually meet and then use the information from the requirements that we stated at the beginning. And as far as our financial stewardship goes, using the minimal funds to conduct the creation of the project and then maintaining it for as long as possible are really going to lower the cost, because it'll make further probes a much less necessary need, and will therefore enable us to spend less money overall and still gather the same amount of data we would if we sent out a probe that lasted less time.
So for deep space missions to become more common, we need the ability to travel through the heliosphere faster, assure sensory resolution and accuracy is reliable, and a robust design is needed to increase system longevity. We're hoping for our system to be able to test and verify all of the aforementioned requirements. Additionally, our design will achieve more efficient power generation and have a greater solar system escape velocity. In the end, this probe will further interstellar research and our understanding of our galaxy. So thank you so much for listening to our presentation, and we hope you enjoyed learning about our probe. Thank you.